Kia ora. We're going to have a look at what anti-differentiation is. So if we want to understand anti-differentiation, which is introduced on pages 52 to 54, we're first going to have a reminder of what differentiation is. So remember, with differentiation, we do two things. We multiply by the power, and then we reduce the power by 1. So that's how we differentiate. So let's do it here. So here we're going to multiply by 5. So that means it's going to be 5 times whatever it is, x to the power of whatever, over 40. So we multiplied by the power first. We multiplied by 5. And then we reduce the power by 1. So we get that number there, the 5, and we reduce it by 1. So it goes to 4. Right? So then let's do that again to the next thing. So remember, we only deal with polynomial differentiation in level 2 calculus. So it's the same thing with anti-differentiation. We're going to have to anti-differentiate only polynomials. So things that look like this. This is like as complicated as it gets, pretty much. Okay, let's do it to this one. So remember, we multiply by the power. So I'm going to keep that minus sign. 3 times 4 is 12. And then we reduce the power by 1. 12x to the power 3. Over here, we've got plus 15x squared. Now, something I do want you to notice is here, remember, if it's just a constant, it just ends up disappearing. So this goes away, or disappears. Oh, I don't know how to spell that. 2 S's, sure. It disappears. So there is nothing to do with that plus 1 anymore. It's gone. Right? So let's just simplify this. 5 over 40, we can simplify that to x to the power 4 over 8 minus 12x to the power 3 plus 15x squared. So this is how we differentiate. Right? Now, to anti-differentiate, what we are going to do is we're going to just do the opposite of differentiating. Now, in maths, when you're doing opposites, you need to unpack it. Right? And we're going to unpack it by doing the reverse steps in reverse order. And that will make sure that our anti-differentiation works. So before, we multiplied by the power and then we reduced the power by 1. So what we're going to do is we're going to reverse those steps and do them in reverse order. So instead of doing this, we'll start and do it backwards. So we would finish off by reducing the power by 1. So what we're going to do this time is we are going to increase the power by 1 first. Increase the power by 1 is going to be our first step for anti-differentiation. And then we'll just do the opposite of this. So instead of multiplying by the power, we will divide by, and we've already done this step, so I'm going to say divide by the new power. Right? So this is going to be how we anti-differentiate. Right? And all it is doing differentiation, doing the reverse steps in the reverse order. That's all we're going to do. So what we're going to do is let's anti-differentiate. I'm going to cover up what we had before. Let's anti-differentiate the answer that we found before. Whoopsies, I forgot to put a dash here. That's very important. So we had f of x, and then we differentiated to get to f dash of x. So let's start with f dash of x. So we're going to anti-differentiate our f dash of x equals x to the power 4 over 8 minus 12x cubed plus 15x squared. Why am I confused? No, don't worry. I'm confused because I missed a dash up here. Blimmin' heck. What a numpty. Remember, this was our original function before, and we differentiated to get this function here. So what we're going to do is we're going to anti-differentiate, and we hope to get the same answer as we started with, because we're doing the opposite steps, right? So let's try it out. So first thing we're going to do is we're going to increase this power by 1. So to find the function, the original function, we're going to increase this power by 1. So it's going to become x to the power 5. And then we're going to divide by the new power. So we're going to have to divide this, so it's over 8, divided by 5. So we could do a big fraction and write over 5 here, but instead I'm just going to do times 5 on the bottom of the fraction to save some time, because it's doing the same thing in maths. Okay, so let's do this next one. This next one's going to be a better example. This one's a little bit complicated, to be honest. This next one here, so it's going to be minus and then 12x. We increase the power by 1 first, so it's to the power of 3 currently. So we're going to increase that to a 4, and then we're going to divide by the new power. So we're going to divide it by 4. Right, and then after that we are going to do this one here. Plus 15x, increase the power by 1 to the power 3, and then divide by the new power. I've run out of space, don't worry, I'm just going to let the book up so I got some more space. Zoop, zoop, zoop. Okay, let's simplify. So f dash of x, the original function, is going to be x to the power of 5 over 8 times 5 is 40, minus, and then over here 12 divided by 4 is 3, so it's going to be 3x to the power of 4, and then over here 15 divided by 3 is going to be 5, plus 5x to the power of 3. So now we have our original function again. Let's see if these reverse steps work. So x to the power of 5 over 40, original function, nice, x to the power of 5 over 40, minus 3x to the power of 4, minus 3x to the power of 4, nice, plus 5x to the power of 3, matches, yes, plus 5x to the power of 3, and that's it. Oh, hold up. So, we've still got this thing here that's missing. So this has totally disappeared. This plus 1. So we had this here, but what happened was when we differentiated, it disappeared, and then there was nothing here for us to manipulate and get that back. So actually, when you differentiate, you lose constants. Anything that's a number without an x attached to it is disappearing, right? And we need a way to make sure that that thing, if there was a constant there, that we get it back. So what we do in calculus is we just write plus c, where c is the constant of integration. Constant, oh shucks, you don't know what integration means. Of integration. Integration is the fancy word we're going to use for anti-differentiation in the future, but I'm just going to use it now. This c is just in case there is a number in the original function that disappeared. So it covers our backs. And this number could be anything, and in our next class I'll show you how we can find that. Now, I just want to explain that plus c really quickly. So we're going to go over to Desmos here. So we've got our original functions here. We've got f of x equals x to the power of 5 over 40 minus 3x to the power of 4. So it's the same function we're working with. So the function is in black, and our derivative is this in blue here. Right? Now the thing I want you to notice is that if I was to get rid of this, I want you guys to look at the blue dotted line. Notice that if I change the 1 to a 2, the blue dotted line actually stays the same. So what we're going to do is we're going to make it a C. And we're going to add a slider in. No matter what my C value is, it doesn't actually affect the derivative at all. So that C value could be anything in the original function, and the derivative will still look the same. Right? So this constant here, any constant is not going to affect the derivative. So therefore, if we're anti-differentiating a derivative, we're not going to be able to find that C value unless we have some more information. Right? So that's from probably the big idea of anti-differentiation. Always remember to put this plus c in when you are anti-differentiating. It's really important. Okay, let's have a look at a few examples, just so that you can, know what to do when it comes to the questions in the workbook. So we're going to have a look at, say we have a derivative, and it is, we're going to go x minus 3. So we want to anti-diff this. Do some anti-differentiation on this. So f of x, all we do, the steps are, what was it again? Number 1, we increase power by 1. Number 2, we divide by new power. And in fact, I'm going to add a third step, plus c. Very important. Okay. So f of x, we've got here x, so that's the same as x to the power of 1, right? So we're going to increase the power by 1, so it's going to be x to the power 2, and then we're going to divide by that new power, divided by 2. Now, minus 3, that's the same as having x to the power of 0 secretly there. So it's going to be minus 3x, and then that's going to be to the power of 1 now, because we are increasing the power by 1. And then it's divided by 1. And then remember the plus c at the end, so the function is going to be x squared over 2 minus 3x plus c. We can always double check by just finding the derivative again, and we can check if it works. So let's just do that now. We're just doing a little check. So f dash of x would be, this is honestly, I find it so hard going back to doing differentiation rules after you've been doing some anti-differentiating. Okay, so originally we multiplied by the power, so that's going to cancel out this 2. So we're going to multiply by 2 and then reduce the power by 1. So that's just going to be x. Yep, nice. And then this one here just becomes minus 3. That c disappears because it's a constant. So voila, it would take us to x minus 3. That's what we started with here. Should I do one more example? Let's do a trickier one. Let's say we had, the questions might look something like this. Anti-differentiate. We're going to go with cx plus x squared over d. So that might be your question. So I might do an arrow. If they don't have any notation, which is often the case when we're using anti-differentiation in level 2, in the future you'll start using this integrand symbol, which is beautiful, but for now sometimes they'll give you a question without any notation, so you might just do an arrow like this. So let's follow the rules. We'll increase the power by 1, so it's going to be cx squared, and then divide by the new power, divided by 2. And then this one here, we'll increase the power by 1, x to the power of 3, and then divide by the new power. We learnt that trick before, that we can just write 3d. Ooh, and we need to do our plus c. So that's all you need to do for anti-differentiation on page 54.